Я хочу сказать спасибо организаторам. К сожалению, я не могу говорить по-русски, но what is gonna be in English? Okay, so let's begin. As you know, our task is suggested around 30 to study algebraic structures from the point of view of model theory. He thought that if logic is important, that we trust foundations of mathematics, it might be important also to study algebraic structures like rings, fields, groups, and so on. In this talk, I'm going to be interested in model theory of groups. And the first examples I was suggested to study are free objects in varieties. Free abelian groups, free groups, and so on. You already heard me talk with version about abelian groups, not only what's called free abelian, but for general abelian groups, using what's now called log invariance. This was talk about free groups. On the other hand, for free groups, it took much longer. It took the contribution of many people. Lyndon already studied model theory of free groups in the 60s. Montserrat, McCammon, Rasvoro, Renes, many people was contributing to the study until 98, when Karampovich and Montserrat, they provide a description of finally generated groups which are universally equivalent to free. And finally, in 2005, the big problem was solved by Karampovich, Montserrat, and Sela, and they provide the description of finally generated groups which are elementarily equivalent to free. This theory still is developing, and there's a lot of work to do. Sela, for instance, showed that the theory is in fact stable, and it was a very celebrated result in model theory. They were very happy. And there are many open problems yet in this area. So what I want to talk about is a project that some of us are involved in, Norovich and Andrew Duncan, which would be to study model theory of a class of groups that in some sense contain both extremes. Free abelian groups and free groups. And this class of group is called partially commutative. So this is the general concept. So what is class of groups, partially commutative? They are very easy to describe. They're described by presentations. And the only relations we allow is some of the generators to commute. And it's customary to associate the presentation to a graph. This is a very good way of encoding the presentation. And this encoding is done the following way. Given a simplicial graph, we associate a presentation as follows. We put in one-to-one correspondence vertices of the graph with generators of the group, and then we take a convention. We send, for instance, two generators commute if and only if there is an edge in the graph. If I take this convention, I'm going to say that this is the commutation graph in the presentation. If I take the other convention, say that two generators do not commute if there is an edge, then I'm going to give you the non-commutation. Okay, so this is the class of groups we are going to be interested in. What are examples? We have seen some of them, but I want you to see the relation with the graph so that you get them familiar. So in here I have three vertices. This means that there's a free generated group. There are no edges. This means no relations. I'm just defining you the free group of rank 3. Again, three generators, all of them pairwise commute. I'm just giving you the free abelian group of rank 3. Okay, these are no difficult. You have two generators that they don't commute, another two generators that do not commute, generate group, and both of them commute with each other. This is just a two person. For example, you have a free abelian group of rank 2, free abelian group of rank 2, no edges between them. This means it's a free product of two abelian groups. But in general, there is no decomposition. You cannot expect that your group is going to be decomposed as a free product or a direct product. It's just a presentation again. This, in this case, is a 5-generated group where every vertex commutes with the previous one. So 1 commutes with 0, 4, and so on. This is the type of group we want. So they occur in many places. I'm not going to go all over. I just want you to have the feeling that they are natural, and since they're natural, they appear. They appear in algebra, we call them partially commutative. They appear in computer science. They call them graph groups or traceable nodes, they appear in physics, and they appear in theory. In theory, they are also called triangular groups. And lately, became very, very fashionable because, as you know, that Leonardo solved a very important conjunction of the manifolds with the virtually private conjecture. And the idea is that he showed that very rapidly all fundamental groups of three manifolds up to finite index, you can see them as subgroups of this type of closed groups. So what it says is that they are extremely rich in subgroups. So don't let me mislead you. If a billion groups have very easy subgroups, they are a billion. Three groups have very easy subgroups, they are three groups. These guys contain many, many, many subgroups. Many of them, they have one. If you want to think, they are set to possess two, so you have a lower subgroup and so on. That every free manifold is happy. That's not happy magically. If you want to find it, it's a bit easier. That every free manifold can be done as a two manifold and a circle.
But conjecture.
That every free manifold is of this type. So you got a two manifold, you do times a new, and then you it's a strong form of concurrence. Alright, so this is the class of groups we are interested, and the problem I would like to talk today is the classification up to universal theory, restricted in this class. So I want to understand one partially commutative group is universally equivalent to one. This is the model of the question, but I'm going to use characterization, the algebraic characterization that was given by Hermes in communication of three groups, and then in general for recursionally structures by the Yarman reciprocal. Namely that these groups are equation Euclidean, and then they are universally equivalent even only if they discriminate each other. I know that in this audience you're quite familiar with this notion, but just want to recall you fast. By discrimination I mean that given any finite set, I can find an homomorphism which is injected in this finite set. So if you think this way, I can take bigger and bigger sets, and what I'm saying is that I can see the sets in the image in the other one. So I'm approximating one group with the other. It's a type of approximation. They also call limit groups, and this is the type of viewpoint I'm going to. All right. So before I'm stating the result, I want to give you some examples so that you get a bit of feeling of what's going on. 3 billion groups, as I said. Alexei described them very nicely, so we understand them well. I want to understand when a partial commutative group is universally equivalent to Z. We know that it's going to be a billion, the torsion free finally generated, so it has to be free equivalent. All right, easy. And if I want to show you, you have seen this proof many times, I just need to show you discrimination. That is a subgroup from so much discriminated. And if I want to discriminate Z2 and Z, I can give you the following family of homomorphisms. You send A to A, and B to the power of A. This is a parametric family, and this family is sufficient to discriminate many elements. Choose everything off, we're fine. And this example can be done more generally in this class of groups. So let's do the same thing. Imagine now I'm taking a free product of the groups, and I want to discriminate it into the free product of Z. Okay, that's just so that this is generated prime, and this is generated prime. So what I'm going to do, a generic element here, I can put it like this. So what I need to do is I'm going to take this family of homomorphisms from this copy of Z to Z that discriminates this component. Another homomorphism from the second copy to Z that discriminate these guys. These two homomorphisms induce a homomorphism from the free product to the free group, and it's going to be injected in this element because it's not going to kill any of these components. Okay? So the idea I want you to get from this picture is that we can do this more general. So what do we do in terms of groups? We need to increase this ability. What do we do? In Z, we replace one vertex by a complete graph, a clique. What we do in the second case? In the second case, I have 2 vertices, and I replace each by a clique. All right. So what do we do in a general graph? You give me a general graph, and I take every vertex. I can replace it by a clique, in this case, a complete graph. And if the vertex is connected to another one, every element in the clique is connected to everybody else in the other clique. inflation. I just make a billions bigger. This defines, the simulation graph, and so another group, partially commutative group. Okay? If you have followed a little bit this type of proof, I take normal form, I discriminate the components using this type of thing, I leave the homomorphism. The same type of proof works for this type of graphs. So my claim is that it's easy to show that the inflation of a graph, the group defined by the inflation of a graph, is universally equivalent to, to the group defined by the graph. It's just this type of general equation. All right, we learned something. The question is, are we done? Is this all what can happen? And the answer is no. Okay. So let's go now to the other side of the spectrum. Let's see what's happening in free groups. We know free groups are universally equivalent, but the reason is not about the variance. It's because they embed into each other. Now, when you have an embedding, this is a sample of this one, every universal sentence in the big group is obviously true in the subgroup. So you have a diverse inclusion of theories. And if you have double embedding, then you learn that the universal theories are the same. And this is not only a phenomenon of free groups. So this is the path of graphical function before. I'm not showing you these embeddings, but believe me that you can embed this group into the path of rank 5, and again back to the path of rank 4. Now again you have double mutual embedding, you have equality of universal theories. Okay? So let's see. We have seen that increasing abelians is going to be necessary. It happens for the abelian cases. Mutual embeddability, of course, is going to be necessary operation. It happens in free groups. Are we done? And the result I want to talk is that yes, we are done. So if you want to understand when two partially commutative groups are equivalent, it suffices to, up to inflation, see one in the group as a subgroup of another one and vice versa.
And there's no.
And it's fixed, yeah. It's you can bound it by the product of number of vertices of both. Okay. This implication, I hope you will believe it. Because as I said, inflation does not change the universal theory. And then the embeddings give you double embeddings, subsets of the theory. So this implication is easy. If I want you to explain the other implication, I need to understand the problem of embeddability between partially commutative groups. The good thing is that at least we have taken a problem which was model theoretic, and we have reduced it to one which is algebraic. And we hope to have tools that will address this problem. Okay. So I want to understand when a partially commutative group is a subgroup of another. It will be a very easy question in this class. And if I want to really prove the theorem, better the condition be able to be expressed in the universal sentence. Because that's the only thing I have. I'll have universal sentence. So that's what I would like to do. So again, I would like you to have a feeling of what's going to happen next, that it doesn't look really strange, and I want you to practice a little bit what are the embeddings. Okay, I'm going to give you groups, and now to confuse you a little bit more, I'm changing the convention. So if you see an H now, I want to think that they do not commute. I'm changing convention, because I know that I'm going to have too many H's. Okay, I give you this group. And I give you the obvious map. A equals to A, B equals to B, and so on. B equals to E. The question is this an embedding? That's easy. It's not an embedding. I'm telling you this is not trivial here, but the image does not have an H, it's going to be trivial. So this map would give me this commutator. The commutator of B is going to send to this commutator, but the commute trivial is not an embedding. Okay. We have been a bit dumb, so let's try to be a bit more clever. I change my graph, I change my map, and now I'm asking you, is this an embedding? This is already a bit more advanced, you need to think a little bit, and the answer is going to be no, and I want to show it to you so that you see how I'm going to do it in general. You have to believe me that this commutator is not trivial here, it's not just computed. But when you look at the image, you're gonna get regular commutator. So is this commutator, or the commutator is commutator, and this one, if they are not connected, this is one. So the feeling I want to have is that when we check embeddings, usually there are some of these commutators that either are killed, but if you don't see the obvious ones that are killed, then you say, okay, I'm an embedding. So this is the type of statement that you get when you work. That's the philosophy you have. There is a finite set of commutators which are going to witness if something is an embedding or not. And I'm going to make this more precise. So I wanted to say that there is a finite set of commutators so that a map is an embedding even only if it's injected in this set. Now in here, you should be outrageous. But you are lying, and you would be right, and I'm lying. And I'm not doing it on purpose, it happened to me, the mistake, and I got, oh, what did I do? Why is wrong? Well, let's see this example. You have an abelian group. All commutators are trivial. Abelian group, all commutators are trivial. Clearly, any map is going to be injected in the commutators because it's already trivial. And I'm not going to convince you today that I'm going to give you embedding from set 2 to set. So something you know. I went over the proof, and this is what was going wrong. At some point, when I had a map, look at this map. I don't have motion, but x is sent to a to the n, y is sent to a to the n. The image of generators have a level, in this case, t. And in the proof, I was saying, look, I mine universal equivalence, and I showed you that I can make my abelians bigger. And by making my abelians bigger, I can assume that there is no repetition of letters in the image of generators. So the operation of making an abelian bigger allows me to assume that the image of the generators have disjoint outcomes. Let's call this type of map thing. So a map is saying if the image of generators have disjoint outcomes. And now I'm fine. Now this proposition is, I'm not lying. So if you give me the fact that a K map is an embedding is controlled by a finite set of commutators. So the image of generators have disjoint outcomes. No letters in common in the image. If a letter appears in the image of a generator, this letter does not appear. So under these conditions, then it's true that a finite set of commutators controls the fact that something is an embedding. All right. And now I hope that you will get the feeling why this is true. Okay. So universal equivalent, even only if existential equivalent. Fine. Now the existential statement is going to show me that the existence of elements injected in this finite set. I can say there exist an element, so this commutator is trivial, and these others not, and these other is, and these others not. Okay, how do I make the map tame? By increasing abelians. I increase abelians, I fake generators as much as I need in this type of procedure, and I make it tame. Once I have injective plus tame, I have embedded. Right? Okay, so where we are. We have shown that universal equivalent reduces to embeddability. And just careful about the set, because at the beginning, the first time I gave the talk, people were thinking that this set would be very easy. Okay. Commutators, generators, or weight one. And the set can be as complicated as we want. This type of example, in here I can make the weight grow. And actually, right now I can't find it, so I don't know an effective value. You know, it's fine, but I cannot find an effective value. Okay. The last day, so I'm going to make the story short. We have reduced the problem to embeddability, and I want to understand embeddability. And there was a conjecture that was trying to relate the embeddability of the group with some graph embeddability. Okay, who's this guy? I'm not going to define it, but it's a graph that you obtain from gamma. It's an infinite graph, and it's not locally finite. You get with this graph, and there is a way of producing this huge graph. And the conjecture was that the embeddability was controlled by this type of graph embedding. And Kiman-Kobayashi conjecture, and they proved that in some cases it's true. For instance, if the graph does not have triangles, conjecture is true. The embeddability is controlled by graphs. We show that on the front of it you have a problem, I shown that it is decidable. So if you give me these two tasks, there is an algorithm that decides whether or not this is a subject of this. This is related to graph search. So, what's the conclusion? For the cases where the conjecture holds, we can decide the problem of immutability. And since we can decide the problem of immutability, we can decide the problem of deciding if two groups are universal. So this is the summary. In some cases, for instance, if the graph does not have triangles, the problem of deciding if one is a subgroup of another one is decided. All right. And then we can also decide the problem of universality. It's an algorithm that given a graph that does not have triangles determines if some other graph is universally equivalent. And the theorem also helps us to get some conclusions, especially in the negative way, on the elementary theory. For instance, think that Cn are cycles, pentagons, hexagons, and so on. I mean, more general, but we don't need to get into the definition because it's different. Now, algebraically, you can check that, for instance, the hexagon embeds in the pentagon, but the other way around not, even if I'm allowed to include. This allows me to conclude that they are not universally equivalent, and so they are not elementary equivalent. And we can begin distinguishing classes of partially equivalent. These are the same class, these are not. Especially if we can say these are not. Okay. So what are our questions? Don't let me lie to you. We solve only this problem when the map was thin, but the general problem of one partially equivalent group is a subgroup of another one is still open. We don't know how to describe it in graphs and working. We don't know how to describe it. Now, I have decided to explain all these four groups because that's what I feel more comfortable, but you can do and ask the same questions in the algebras. It makes sense. You get variety of Lie algebras, you interpret as nature of the commutative for the bracket, you define partially commutative Lie algebras, and you ask one is a subgroup, one Lie algebra is a subalgebra of another. And the question is still open. In terms of algorithmic, I showed you that to decide the immutability problem, there exists this finite set of commutators. The problem is I cannot effectively bound the weight of the commutators. If one would do that, the problem would be decided. And in general, the general problem we don't know because we don't know how, when. And in here you have to be careful because they seem very interesting problems. If I formulate them in the context of monoids instead of groups, they have very different answers. So for monoids, the first problem would be decidable, while the second problem for monoids, it is undecidable. Understand, groups are not the same as monoids, but we have to be careful with the possible solution. And finally, as I said, it helps us to bound, to reduce also the elementary classes. So for instance, in the case of cycles, we can reduce using this universal classification that if a partially commutative group is elementary equivalent, it's forced to be of this type. So I can add edges here of type 1 everywhere, heard it, but nothing else. So now the question is this elementary equivalent? That's it, can help we found it. And I think that with this